Just starting the recording. So the lecture content from here on out is a little more, I guess, it's not as math heavy. It's a little more tips and tricks that have to do with the lab, just working in labs in general. Lab 6 will be about computer control, but I feel like it's something that, one, you guys have been using throughout all of the labs beforehand. Just trying to get, like, when National Instruments isn't working or the GPIB communication isn't working. So that's, you should be familiar with that already from the previous labs. And then also I feel like the computer control that we talk about in the lab, or what you'll be working through in lab 6, has more to do specifically like with the instruments that you're using. But I feel like this is something that we're exposed to also in our everyday life, of just trying to get like Bluetooth or certain connections working between computers, or even just like video bus cables, and having the right inputs and outputs, or communicating that. Whenever the layout of these lectures were designed, I think it may not have been as familiar, but I feel like it's something we run into everyday life, but this will give it more of a historical context as well in relation to the types of instruments you run into in the lab. So with this, what we're talking about with computer control is, like I mentioned, the hardware type of that you've been using in the lab to send data from one piece of instrumentation to your computer. And we've been using the GPIB since that's what's with most of the instruments that we're using in the lab, but over time and over history, like, it's been updated for cheaper connections, faster connections. So what I've listed on the screen here is kind of historically what it's gone through to USB, and even today, having a wireless bus between instruments with Bluetooth and the like. And then in terms of software, I mean, I know a lot of you guys are taking the computational physics course, so working with Python, lots of different computer languages, and also those of you guys in engineering physics. So you guys have been exposed to a lot of these different softwares already. And in our lab, we've been using MATLAB, National Instruments, and with tomorrow's simulation, a little bit of LabVIEW. And then finally, we're going to be going over in some detail just with the GPIB bus, where the bus just means a way to carry information or bus information from an instrument to a computer. So we've been using the GPI to USB bus for some of the instrumentation, where this PCI here is just the interconnect between some instrument and then the motherboard of your computer. So in the back of the desktop computers we've been using, sometimes you have to install a PCI board or slot. I've had to do it for working with the cameras in my lab for video connections or network connections. And it's important when you're installing these type of PCI cards that you stay grounded and you don't short anything on the card itself. So actually with the computers that are in the lab, it has a USB connect, so actually we don't have to install this. But if we wanted to install the GPIB directly to the computer, we'd have to buy one of these PCI cards. This is also something to consider if you're working in an experimental lab. If you're buying a desktop, you're working with instrumentation. Now desktop computers are so small, and laptop computers or tablets are so easy to use that it's very easy to just say, oh, I'm just going to buy the top computer, it's going to be condensed and stuff. But if you're working with instrumentation, you actually have to consider, like, are there open slots that I can install my video cards, my data processing cards, when you're doing experimental work. So when we've been using the GPIB, if we were doing lab 6, actually in the lab, we would take a look at all of the communication pins that are in the GPIB, which stands for General Purpose Interface Bus. So the general purpose just meaning that it works with a lot of different instrumentation back in the 80s. And could interface with them and then bus that information there. So just be aware that in the back with these different pins, they actually have different purposes. 8 of these pins are for data, 8 is for grounding. 3 for handshaking is just for the computer and the instrument to recognize one another. And then some of the control of transferring the data. So you could actually go and look at the different pins and know what they're actually used for, and try to, if we were working with the instruments, actually ping these pins and make sure that they were working correctly. So this was the list for 1 through 12. This is the one for 13 to 23, where you could see these are all grounding for different wires that are within the GPIB cable here. If you guys took a look behind in your lab stations, you may have noticed that we had multiple of these GPIB cords, that they're kind of unique in the fact that they have both male and female connections on both the input and the output. So you can actually form like daisy chains and branch these devices between one another and still have them communicate with the computer. So that was pretty nice that we wouldn't have to worry about the order that they were connected in the back to actually work. And I think most of you guys were looking at those connections, or I think most lab groups ran into an issue at least once or twice in lab and actually looked at those connections to double check them. So as I mentioned, GPIB we're using because it works with the instruments we have, but it's more of a historical bus. When I was looking on YouTube just for fun to see what they had on GPIB, they actually have this tutorial from a VHS tape that was made in 1988, so quite old, or this person working with like one of the HP function generators or instrumentation that looks familiar like in our lab, but they were brought back an old monitor screen and said that they were data logging like it was 1982. So I just thought those were funny examples that it's an older technology and that there's all these different generations moving up to different types of buses that you may encounter. But I would say working in experimental labs, you might end up working with historical instrumentation, and you would have to be aware of these different types of buses. Like one of the lasers that we just bought, we had to buy an RS-232 cord to be able to USB to communicate with our desktop computer, but also, and that's brand new instrumentation. And even with new instrumentation where you think they would have updated these types of buses, they stick with what works. So I was just actually, before the quarantining, back in February, I visited my friend who just started a lab at Oberlin College. And she was showing me her brand new fancy, like $80,000 piece of equipment for doing capillary electrophoresis. She's in the chemistry department. And I was like, hey, I recognize that bus between like this big black box type of equipment, and it was GPI communication between the computer and her instrument. So I was like, it still comes into play because with very specialized equipment, it would take them more time, money to change things over instead of working with what's compatible and what's been working for them for decades. So you might still run into this type of bus technology. So that's a little bit about what would be, we'll see what Lab 6 turns into, but that traditionally would have been the first half of Lab 6 of looking at using the GPIB control and actually communicating from the computer to the instrument, so you can actually bus information that way and actually write little programs for and control your equipment from the computer. So I'll probably go into that in more detail next week. But also with some of the control of we would actually do an experiment in Lab 6 of doing temperature control with different types of feedback and control algorithms. So, I mean, there's an entire area of engineering of control systems, of writing these algorithms, of controlling instrumentation and equipment in factories and writing algorithms. So like control systems will be an entire course in electrical engineering, for example. But we're just going to talk about some very simple systems or control algorithms that you could control your equipment with. And for an example of what we'd be doing in Lab 6, but also in many other types of examples like as simple as the thermostat in your house or heating up an oven would be controlling temperature with these algorithms. So the first one that I want to mention is a very simple on-off control. So it's sometimes called bang bang, or I think of it like when I'm trying to go to sleep and I hear my thermostat like click on and off with the temperature. What that is, you have a set point for a temperature. Like let's say this is an oven, you want to heat it up to 150 degrees Celsius, and then maybe later you want to heat it up to, looks like 175 or so. So this red line here is your set point, and we just have two different phases here. And then this blue line here would be turning on and off the power source for your heating element here. So when the temperature drops below your set point by a certain level, you say, hey, turn on, and then it'll increase above there. Once it increases above a certain point, it'll turn back off, and there's just a binary option here. So you can see with the actual temperature that occurs here, you have a lot of oscillations if you're using this very simple on-off control. But a lot of equipment uses this because it's very simple and it's inexpensive as well. So that's why thermostats will use that, ovens in your kitchen will use that because it's inexpensive. But let's say here we're having fluctuations as much as, looks like 10 degrees above the set point here. If you have something that's much more sensitive, like let's say for many commercial products, maybe having this high of a temperature, drying a certain type of paint or so would cause damage to it. You might have to have finer control. So an additional control algorithm would be proportional control. So instead of just having this binary option of 0 or 1 to control if it's on or off, you can say, oh, I only wanted the power to be 10% or 20% or 30% because we're not that far off, versus if you're way off, let's crank it up to 100% of the power capabilities of our heating element here. So this means that it can be variable, it can be proportional to the difference between your set point and what the actual temperature is. So this text here, I'll upload the PowerPoint and the notes, but I would say with this example of an oven, or if you were working in lab, you wouldn't be heating up to 175, it's a little sample holder, so it would be 40. But here I'm saying for that plot I showed, you want to reach 175. So you might have a band 10 degrees above or 10 degrees below, and if you're 1 degree away, you only do 10%. If you're 10 degrees below or greater, then you would use 100% of the power. And then if you're above there, you can keep the heater off. You can have this be proportional. So how we'd write this mathematically is the power applied would be some amount of gain based on the difference between that set temperature and the observed temperature. So the larger the difference between these two, the larger the amount of gain that you would get. The smaller you would have a proportional amount. So this is an example plot of showing, let's say this red line again is our set point temperature, and then if we use proportional control with different amounts of gain, so this value P is different, we would see different responses here. So with the lowest value, we may actually never reach that set point because we'll never reach the full power applied if we have this less than 1, I guess. And then if you are higher, you can see that you can get closer and closer to that value. If proportional gain is very high, you can actually overshoot and be higher than your set point temperature. But if you have it right in the middle, you're always going to be below that set temperature. And also you see that on average with this blue curve, you're always slightly off from your set point temperature. So there's always going to be this steady state error. And that's because if you look at this equation, if this difference is 0, you're going to be applying 0 power. So that's a problem with proportional control, that you'll always have this slight offset. So the last and best option that I want to mention is called PID control, or proportional, integral, and differential control. So this is a common method in control systems, and it's considered like the gold standard type of method. And I have this block diagram here showing how it works. So we just talked about this proportional control right here. What we're measuring our plant or process here would be like our oven temperature that we're looking at. So walking through this block diagram, what we would have is this R of T is the set point. So this is all time dependent. Just like on those plots I was showing, like temperature versus time. So that's why this is in parentheses with the T. So we have a set point. We have some reading from our oven or our little thermoresistor. And we take the difference between these two, and that's our error between the two. So then we can take this error and either do the proportional control that we just talked about, where we would multiply some gain, this K sub P, times the difference or the error here. So that's a proportion. So how much do we want to adjust, not just on off, how much, like with a linear gradient here, do we want to adjust our input? But then in addition to having the proportional control, we also have integral and differential. So the integral here would be looking at, as we sum up over time, the difference of this error, how far off are we? So this integral would then remove any constant error and would actually correct for that steady state offset that I was showing on the previous slide. So if you're summing it up over time, if we're slightly off from our set point, this will then become a very large component in the error as we sum over time. So that's the power of the integral portion of PID control, is that any slight offset that then would be summed over time can be corrected for. Then lastly, the differential portion is looking at the change in this error over time. And the differential can account for large fluctuations and can damp those contributions down. So this would be similar to on the first slide with the bang bang or on off approach. If you have these large changes occurring over time, this can then damp down any of those degrees of change if you want it more steady. So all of these constants here, the KP, the KI, the KD, those are all the different gain. How much do you want the proportional, the integral, or differential to contribute to your control process here? So you can have all three of them contribute equally for PID control, PID control, but you can also set the integral component to 0. If you don't really care about the offset, you just don't want huge swings, you can just have PD control, or you can just have PI control if you just want to be close, but you don't care about how fast you're making those changes. So with that, you can then sum together all these changes that you want to make, or the differences here, and then this U of T would then be your control that you would then feed back to your oven to make, and then you would repeat this over and over again with time. So with that, here's an example of the plot from the PID control that you can see here. This is how we're controlling the power of our heating element. We have a set point that we don't have those large fluctuations back and forth or any wiggles here, and we don't have an offset that it may take more time than the on-off to actually reach the set point compared to on-off or the proportional control. We can see it's more gradual, it's more steady state, and you have a lot more fine-tuned control with this method. So those three types of controls, in lab 6, we'll do a simulation working through those and getting a little bit more into the math that's being used, but there's like a small, it's not that complicated that we have these equations here of just linear and integral differential with that error compared to the reading and the set point. So any questions with the different types of control at all? Okay. So two last things, I guess, software control when you're working with computers. You guys worked with National Instruments, the NIMAX, to communicate with the instruments in the lab. But also another common software that you may run into in experimental labs is LabVIEW environment. So instead of using a programming language where you're writing lines of text, LabVIEW is also by National Instruments, but they actually use a more graphical based control of instrumentation. So you have these block diagrams that will actually, instead of writing like, let's say in MATLAB, if you write XCore for cross correlation, they'll actually have like a little box and wires between these boxes that represent what functions you want to do. So there would be a correlation box, and you draw a wire between, let's say, the output or your GPIB input to your computer, and your signal will be coming there. You draw these wires, and it's just a very different way of making connections or writing what you're doing with your instrumentation. But they have a lot of interfaces with commercial instruments. And also, I mean, that graphics type interface is friendly to a lot more scientists, so you may run into the LabVIEW type instrumentation control when you're working in experimental labs. So I just wanted to mention those, but also older instrumentation or instrumentation that has a very small audience will probably be more C-based type languages. But I think you guys are actually even more familiar with the programming classes that you guys have been taking. So that's most of what I wanted to cover today, just a brief overview of computer control, but this is what I talked about today is somewhat specific to like Lab 6 and the instrumentation that we've been using in Physics 204 and 208, but it's something that you can learn from or translate to specific problems that you may run into in the future. Like you probably won't be using the exact same type of DMMs and function generators or even the same type of bus cables, but understanding how to communicate with them to troubleshoot problems, that's what I think is like the main thing with computer control is like, what language should I be using, what pin, what software, working through those bugs and problems is, I think, the universal concept to take away from it, that you run into tons of problems experimentally, and it's just figuring those out. So that's pretty much what I wanted to cover today. Shorter lecture. Do you guys have any questions?
When is the next quiz?
Yeah, so the next quiz and the lab are going to be due next Monday. So I'll try to upload some practice questions.
Those are really helpful last time as well.
Okay.
Also, I had a question. This isn't really specific to our lectures or anything that's going on. I guess it is sort of an overlooking question, but I don't know how much you'll know, but having not been physically in lab for like the last two and the one coming up lab, how big of an impact do you think that will be going into the 300 lab next semester? Will there be a learning curve, or do you think it'll be pretty intuitive once we're there?
I mean, I think the only thing would be the lock-in amplifiers.
Okay.
And I mean, I tried to incorporate in the labs, like look at the front panel, look at the back panel, but there are going to be aspects there of just working with them hands-on is helpful. So, I mean, I think Professor Gao, Professor Singer, I think they'll be teaching that next year. I think they're going to be well aware of that. Everybody's going to be aware of that. Like, okay, people who are sophomores this year will need to maybe a little brief interview to the lock-ins and the like. So I think people will be understanding of that. But I think we are lucky in the fact that Lab 4 was more on the software side of things. And then Lab 6, which I'm working through the adjustments right now. It is mainly this computer control type of stuff. And I think since there has been more programming implemented in the physics department across the university overall, I don't think there's anything crazy that's being missed in lab 6. So I wouldn't be too concerned about that. I think just mostly with the lock-in amplifiers, when you guys are in labs in the future with junior lab or senior lab, like I would just ask questions and just be like upfront about that and be like, look, we didn't get to use this hands-on. So I don't, and also the fact that I tried to point out that there's the overload. You don't want to saturate the lock-in amplifier. That I think people would appreciate you guys asking more questions than not asking questions.
Thank you.
Yeah.
Wait, Robbie, what class is this?
Physics majors have to take the advanced laboratory next semester.
Physics what?
I don't know, like 318 or something like that. 302, 305. I don't know.
It's 301 and 303.
301,
Oh.
303. There's a
What they call
seminar.
junior lab and senior lab, but like it's not always juniors and it's not always seniors in those labs. So
There's a seminar and then there's a class, but like this, except I don't know why they don't call it 2 different classes. Why they call it 2 different.
So, never mind.
any other questions right now?
Thanks, Professor.
Okay, sounds good. I'll see you guys
And
later.
Same thing for tomorrow, for lab as last week.
Yeah, I'll just be on there, and if you guys have questions, if you guys want to touch base at the start, that would also be fine. But I'll just be on Zoom, so you guys can work with your lab partners, but then call in whenever you need to.
Oh, thank you.
Did that work okay for you guys?
Yeah.
Yeah.
Okay.
Yeah.
Okay.
Have a good day.
Sounds good. Yeah, see you guys.
Bye.
Thank you.
Great. Thank you.